we started learning about the cathode ray oscilloscope. The cathode ray oscilloscope is also popularly called CRO. In the last class we learned that the heart of the cathode ray oscilloscope is the display tube electrons are generated by directly heated cathode or indirectly heated cathode, and we have a control grid to control the number of electrons that move from the cathode. So, we have the cathode and we have focusing anodes, 3 circular tubes with the potential difference between them. The central tube is slightly at a lower potential than the extreme tubes. Then the electrons that emanate from the cathode gets focused on the screen by adjusting the potential difference between the extreme tube and the inner tube. So, we call this as focus. The control grid controls the number of electrons, and if I have more number of electrons, more kinetic energy will be transferred to the phosphor on the screen and I will have higher output of light, right. So, by varying the negative potential of the control grid, we can control the intensity of the spot. Then we have 2 deflection plates. The horizontally kept deflection plate gives vertical deflection on the, right. So, we give a voltage VH, we also call this as Vy, vertical deflection plates, and we give a voltage difference between the vertically kept plates, which becomes the horizontal deflection, we call this as Vx. And in the last class we learned that if I want to display a waveform, of course we took a sine wave because it is easy to understand, we have to give a special voltage waveform which goes to minus Vx max to plus Vx max in whatever period that we want to make the display. If we do this, and of course we do it every cycle, right, and we display the waveform. If I make this sawtooth wave span 2 cycles, we will have 2 cycles on the screen, right. And we also looked at when the sawtooth waveform goes from plus Vx max to minus Vx max at the end of one sweep, right. One sweep is the time taken for the spot to move from the leftmost in the x direction to the rightmost. At the end of one sweep, if we do not switch off the electron beam would retrace its path, right, and you will see a faint horizontal line that is very distracting, it is not the signal, right. So, what we do is we connect a very large negative voltage to the control grid. So, this is Vg. Apart from the intensity control, the Vg amplifier as another input, which is known as the blanking pulse. The signal itself is known as the blanking signal. When we apply large negative voltage to the control grid, no electrons are permitted to go across and the beam is switched off, right, and the display will become a blank. That is why it is called as a blanking pulse. If you do that, we get a nice display. If my waveform is not a sine wave, it is something else, I will still see something else. If this waveform is repeated more than 20 times a second, we do not see the waveform actually written, we see a very stationary waveform, right. Now, this kind of oscilloscope we learned is called synchronous mode oscilloscope. In the synchronous mode oscilloscope, the horizontal sweep, the sawtooth given to the x input will have a frequency which is an integral multiple of the y input frequency. The whatever voltage we give to the y plates, that frequency would determine the frequency of the x input. Right. There is only one problem in this mode of oscilloscope, we cannot make any measurement on the x direction, because whatever we are trying to measure is the unknown and that unknown decides the frequency of the x input, right. On the other hand, I can make measurements on the y direction in a synchronous oscilloscope, because when we make the tube we can calibrate the tube. I can apply x voltage and see how much the deflection is, right. Let us assume that on the y plates, if I give 10 volts, I get 1 centimeter deflection, right. Then I know if the deflection is 1.2 centimeters, it is 1.2 into 10 volt is my input, which is 12 volt, right. So if I have 1.2 centimeters here, this is 1.2 centimeters, then this voltage is 1.2 into 10, which will be 12 volts. So I can make measurements on the y. So normally what we do is we put a scale, we put a scale also on the horizontal, so that we can make measurements. But in a synchronous mode oscilloscope, horizontal is not calibrated, vertical can be calibrated, right. So people came up with the idea that horizontal also we should be able to make a measurement, which means I must keep a constant frequency on the horizontal, right, and I should be able to select this frequency, right. So the sweep time, the time that it takes for one sweep to occur on the x axis, we can set, let us say I set it as 10 millisecond, right. I put an oscillator, a sweep oscillator, which generates this sawtooth waveform, and I ensure that that particular oscillator would always go from minus Vxm to plus Vxm in 10 milliseconds, drop suddenly to minus Vxm, and in the next 10 millisecond it will rise again from minus Vxm to plus Vxm, right. So when we do that, if my input exactly 10 millisecond or multiples of 10 millisecond, I will get a stable waveform. Let us assume it is not, we cannot always decide my input would be 10 millisecond, it could be anything. Let us say that it is 12 millisecond, right. this is my sawtooth. So, this is 12 millisecond, but because I wanted to make measurements on the x axis, I have generated only 10 millisecond, and if I have 10 divisions, I know each division is 1 millisecond, and if I make 10 subdivisions in each division, I know each subdivision would be 0.1 millisecond, that is 100 microsecond, right. So, I can make measurements on the x axis, but what will happen is for the first sweep I will have this waveform displayed on the screen. So, let me draw that. So, I will have that would be the first waveform, right, up to this point it would be displayed. Now, if I start the sawtooth immediately for another 10 millisecond, the waveform that would be displayed would be starting from here up to here, right. So, I will have the second waveform, I will put it in different color. The second waveform would start somewhere here and end there, right. The third waveform of course would start from here and go to another 10 millisecond. So, the third waveform would start from somewhere here and go to 10 millisecond. We see that the waveforms are not repetitive, each waveform that is displayed is different portion from my signal that I want to see, and in no time I will see the whole screen cluttered with large number of waveforms, none of them repeating. So, I will not even see a stable waveform, right. So, the screen would not show what I want to see. If I want to see the waveform, and the only way that I can see the waveform on the screen is the same portion of the waveform shown again and again and again on the screen, repeated at least more than 20 times a second, right. So, because it is 10 millisecond, I know the frequency is 100 hertz, right, and so it is more than 20 times a second, it is 100 times a second. So, if I choose that portion to be repeated again and again, I would be able to see. So, what we do is we do not start the sawtooth as soon as one sweep is over, we will wait for the same portion to occur at my input signal. So, if I look at my input signal, I have this portion, right, I have this portion, and the same portion I see is occurring here, right, the same portion occurs here. So, what I do is I do not start the sawtooth, I wait for the same portion to come and then I start the sawtooth. So, my 10 millisecond starts here. So, now for the second sawtooth portion, second sweep also, I will have the same waveform. Similarly, when I go to the third, I again wait till I start, right. So, I stop here, I stop here on the sawtooth generator, right. The sawtooth generator becomes a start stop oscillator, it is not a continuous oscillator, and the start signal has to be given for every cycle, right, and the start signal should come from my input signal, and if I want to start at the same point on my input signal, I need two parameters that would uniquely define the point, right. For example, I am starting here, so if I say my starting point is 0 volts, right. I see there is another starting point which is not identical to the previous starting point, which is also 0 volts, right, but not identical to my previous starting point. So, it is not enough that I say that my starting point is 0 volts, I have to say that the slope here is positive. Now, another point I have 0 volts, this is also 0 volts, but I see here the slope is negative, right. So, the starting point can be uniquely defined if I choose these two parameters. I look at the level of the signal at that point, voltage level. I did not choose 0 volts, I can choose another voltage, right. I can say this is my starting point, right. Then I see there are two starting points. So, this is, let us say V1 volts comma positive slope, this is V1 volts comma negative slope, right. So, to uniquely define a point on my signal, I need the level and slope at that point, right. So, the start stop signal, right, the start signal especially, start signal should be decided by the level and slope on my input. Okay. So, if we do that, the same wave portion of my waveform will be repeated, right, and I will see a very stable display, right. Now, the sawtooth generator has to get an input, right, to start the waveform every cycle, right. So, we call this as trigger to the generator, right. So, the signal that I generate and say a sawtooth waveform start generating one wave, right, is known as the trigger. We trigger the oscillator to generate one waveform, right, and the trigger is determined based on the set level and a set slope on my input, right. And because the sawtooth waveform is started using a trigger point, the oscilloscope is known as triggered mode oscilloscope. The synchronous CRO is used only as a detector in certain applications. We still use synchronous CROs, but we use them as a detector, oscilloscopic detectors. We will look at oscilloscopic detectors when we talk about the null balance circuits. The triggered mode CRO is the one which has become very popular, right, and whenever I say CRO, I do not have to say it is triggered mode CRO, you understand it is a triggered mode CRO, right. Now, in life it always happens that we think we have solved the problem, right, but when you solve a problem you always create two more, right. We said okay, we have the same portion repeated again and again on the screen, so that I get only one waveform on the screen, right. So, now I have only one waveform constantly displayed on the screen. Okay. Now, I see that the waveform generator, the sawtooth generator stopped for considerable amount of time at the end of each cycle, right. So, when it is stopped, it is at minus Vx, right. So, it will spend quite some time at minus Vx, which is the starting point, right. So, the spot would always be there, right, the spot will be there for this amount of time, the spot will be there by this amount of time, and so I will see a spot there, right, which is not the signal, and it is very irritating, right. So, again we have the same solution. Instead of generating the blanking pulse at the end, we extend the blanking pulse, right, till the start signal arrives, right. Now, the blanking pulse width will be much more, right. It will start just prior to the end of the sawtooth, and it will extend till the start of the sawtooth signal comes in, right. So, which means at this point, right, because it is so negative, the grid voltage is no negative, the dot will disappear, right. I will see no dot, right. But I told you, when we try to solve a problem, we create two more problems. One problem is that initial dot, okay, by extending the blanking pulse width I can solve that problem. The second problem is, if I am going to start my sawtooth generator using the level and slope of the input signal, right, a particular set level and a set slope, right. I need a circuit to look at the input signal, tell me that a particular voltage level and a slope has occurred, which means I need a circuit to sense the voltage level as well as the slope, right. So, this sensing circuit, so if I have my input to, right, I say I put an amplifier, I have Y input, for the X I put a sawtooth wave generator. Now, this has to have a trigger circuit, and the trigger circuit must get the input from my amplifier, Y amplifier output. Now, this circuit will take some time to sense whether that voltage has come in that particular slope has occurred, right, because you have to check and then decide, right. So, there would be a delay I call this as tau t, right. So, which means the sawtooth wave generator would not start as soon as I send 0 and positive, but it will start after some time. So, I will have a delay which is equal to the delay time of the trigger circuit, right, the settling time of the trigger circuit. So, if I look at on the display, right, I will not see the display like this, instead I would see a signal starting, right, at because I will not start here, by the time I start my Y input would have automatically gone somewhere else, right, it would have reached not 0 voltage, but some other voltage. So, which means any measurements I make with respect to my sawtooth is not going to be really correct, right. So, what we do to solve this problem is that we put an intentional delay on the Y, delay the Y signal also by the same amount that the X signal is delayed, the sawtooth wave generator is delayed, right. So, once I delay this signal then my sawtooth is delayed, but my Y input is also delayed by the same amount. So, they are synchronized, right. I will not have any error in my measurement on the time axis, right. So, the initially people used different types of delay, right, and later somebody came up with a very nice idea of a delay line known as the bucket brigade delay line. So, if you look at most of the oscilloscopes, why most of the oscilloscope, all of the oscilloscope, the delay line would be the bucket brigade delay line. I will talk about bucket brigade delay line when we talk about the internal circuits of the oscilloscope, right. So, once we have the Y input, once we have the trigger circuit, once we have a start stop sawtooth wave generator connected to the X plates, I have my triggered mode oscilloscope or simply oscilloscope or CRO beautifully displaying the whatever signal, right. Now, let us dwell a little more on this aspect. Let us say this is my signal, a distorted sine wave, and I have kept my sawtooth wave generator up to this point, right. This is Tx, the x timing, whatever it is, 10 milliseconds per second, 10 millisecond or 20 millisecond or 50 millisecond. Now, if I set my trigger level as 0 volts, slope as positive, right. So, I have 0 volts, positive slope. So, this is my trigger point, and I will see the waveform. The waveform that will be shown on the screen would be because it ends here. This waveform I will not see, right. Now, let me say I make it double, right. I make my Tx, I will use another color, I make the sawtooth span up to that, right. So, this is Tx1. The waveform that I would see on the screen would be something like this. I will see two waveforms in my input, right. Now, let me say I have kept 0 volts, but I had made the slope negative, right. I made the slope negative. Now, 0 volts, this is no longer the trigger, here is 0 volts comma negative, right. Okay. So, the waveform that I would see would be in, if I assume Tx1, Tx something like this, right. The waveform that I would see would be starting from here, because my starting point is here, I will see whatever is Tx from this point and not from this point. So, the trigger level and the slope decide where my waveform starts on the screen, okay. And if For example, we decide that the slope is positive and this is V level and slope is positive. What do I see now? There are two distinct points that satisfy this criteria, right. This could be my trigger point, slope is VL and positive, this is also VL and positive, right. So, depending upon the circumstances that exist, I may have at one point the waveform to start like this, or I will have another time the waveform to start like this, right. So, it will start here, go through this, or it will start here, go through this. You have no control, right. It depends upon the situations that exist in the trigger circuit, right. So, then what we will see is, for one sweep this waveform may be shown, the other sweep this waveform will be shown, and you will see the waveform moving like this, right, which means this slope and trigger that you have chosen, the level and slope for the trigger that you have chosen is not uniquely defining a starting point on your waveform. So, one way is reduce this level, right. Okay. So, I reduce the level, then my starting point is very clear, right. If I reduce that level, then the waveform, I will get a stable waveform on the screen, which would be something like this, right. It starts here and this, right. Okay. Now, so if I look at the trigger circuit, I have the level, I can set the slope, okay. So, now we look at the y input and the x sawtooth. In order to see different types of waveforms, right, the manufacturer would obviously want to give you as much flexibility as possible, right. So, if I put only 10 volt equal to 1 centimeter, I can only see voltages which are in the volts range, right. When I have 10 volts is equal to 1 centimeter and I have, let us say, 1 millivolt or 10 millivolts, 10 millivolts will correspond to 10 by 1000th of a centimeter, which is 100 micron, right. 100 micron shift nobody can really see, right. More than that, the width of the beam itself will be 200 300 micron, okay. So, we would like to have the corresponding voltage to deflection on the screen changeable. Fortunately, that is very easy. All I need to do is change the amplifier gain. Let us say when I had amplifier gain 1, it was 10 volts per centimeter. Now, when I put the gain 10, right, when I make the amplifier to have a gain 10, I have 1 volt itself will give me 10 volts and 1 centimeter, right. If I apply one input of 1 volt, that would give me on the amplifier output of 10 volts, that would give me 1 centimeter. So, by simply adjusting the gain, I can get the deflection sensitivity I want, right. Now, I have introduced a term deflection sensitivity. It is the output deflection on the screen for a given input voltage, right. We normally call this as volts per division, because the scale will be in divisions, right, and most of the time the oscilloscope one division is approximately 1 centimeter. So, some manufacturers also call this as volts per centimeter, right. So, in the y axis, by simply changing the amplifier gain, I can get whatever deflection sensitivity I need, right. Again, over the years several decades now. All the manufacturers of oscilloscopes have come together and then they said, okay, we will make this as a standard, right. So, the standard is that the sensitivity, Y sensitivity, will be 1 to 5 sequence, right. So, it could be that we have 1 millivolts per centimeter. The next set level that you will get on an oscilloscope would be 2 millivolts per centimeter. The third selection that you will get on the oscilloscope is 5 millivolts per centimeter, then it repeats, right. I will have 10 millivolts if it is in millivolts. So, I will have millivolts, 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 10 millivolts, 100 millivolts and 1 volt, 2 volts, right, all are per division, right. So, you will see invariably on your Y input scale, right, the sensitivity kept in terms of 100, I have left one more here, sorry, 200 millivolts, 500 millivolts, 1 volt, 2 volts, 5 volts, right, something in that sequence. Okay. The X sensitivity is given in terms of seconds per division, right. This again is 1 to 5 sequence, right. So, it could be starting at 100 microsecond per centimeter or per division, 200 microseconds, 500 microseconds, 1 millisecond, 2 millisecond, 5 millisecond and so on, right. So, this would be in milliseconds per division, right. So, in a CRO you will always see these 1 to 5 sequence, and for most of our applications is extremely satisfactory. So, no one has come up with any change on this standardization. Okay. Now, if we look at the sensitivity, right, most common oscilloscope would start with 5 millivolts, 1 millivolts is little difficult to get, right. So, if you look at normal low cost oscilloscope, it will start with 5 millivolts, end with 5 volts, right. So, this would be the start point and this would be the initial point. Okay. The X sensitivity would start somewhere around 50 microseconds and will end at 5 seconds. This again is more or less standard for a low cost oscilloscopes, right. The once I have an oscilloscope, right, it depends upon the electronic circuit I put in the amplifier, the delay, the trigger, the sawtooth wave generator, their ability to respond, right, to whatever changes I make in my input signal, right. So, if I look at the Y amplifier, the amplifier would have a bandwidth, right, the amplifier would have invariably a bandwidth. What is the bandwidth? It is a maximum frequency that the amplifier can amplify, right. Generally when we talk about bandwidth, we talk about the 3 dB bandwidth. the minus 3 dB bandwidth, which is also known as half power bandwidth. Because when I look at an amplifier, let us take a typical amplifier, its response with respect to frequency f to its gain V naught by V I could be something like this, a low pass characteristics, right. Then what we do is, we should say that the amplifier passes up to certain frequency f and stops passing the frequency beyond that point, right. So we have to choose a cutoff frequency, and this we declare is the bandwidth of the amplifier, right. So we must be fair enough in deciding this cutoff frequency, right. One way to look at is, okay, I have my power in my signal. If my power is less than half, I say it is no use, right, it is lost. If my power is more than half, I say that signal is useful to me, right. So I choose the cutoff frequency such that at that point the power that is expected is 1 by 2, right. Okay. If we do that, then we call this bandwidth, the cutoff frequency selected, as half power bandwidth, right. And power, when we talk about in small signal level, we always express in terms of decibel, right, the power gain. So we have the power gain as 10 log P naught by P I, right, output power to input power ratio, and when P naught by P I is half, this works out to be minus 3.010 when P naught by P I is equal to half. So we also call this as minus 3 dB bandwidth, right. So minus 3 dB bandwidth or half power bandwidth are one and the same. But when we talk about oscilloscopes, right, oscilloscopes, we want an oscilloscope to make measurements, right. When I want to make oscilloscope, when I use an oscilloscope, I am going to make measurements, right. If I choose my half power bandwidth, right, power ratio is half and power I know is proportional to V square, right, which means the V naught square by V I square must be half, or V naught by V I must be 1 by root 2. So which means if this is 1, gain is 1 here, this point is 1 by root 2, right. At the cutoff frequency the value would be 1 by root 2. 1 by root 2 is 0.707, which means if I have a signal whose magnitude is 1 volt, the oscilloscope, because of the bandwidth problem, is going to show me as 0.7 volts, right. What is the error? Measured value is 0.7, true value is 1, right. So 0.7 by 1 by 1 into 100 would be 30% error, right. So we cannot really make this as a measurement. 30% error is too large in any measurement. So when we talk about the bandwidth of the oscilloscope, right, we do not use the conventional 3 dB bandwidth, because 3 dB bandwidth is useless as far as an oscilloscope is concerned, right. Please note, then when we talk about the bandwidth in an oscilloscope, it is not 3 dB bandwidth, right. So, bandwidth is normally given in terms of 3% error or 5% error and not 30% error, right, half a dB or 1 dB bandwidth. Right. So, we have the triggered CRO having a bandwidth, right. Typical examples are 50 megahertz, 60 megahertz is the lowest that you would get today, right, which can go all the way up to 2 gigahertz bandwidth, right. So, bandwidth can start somewhere around 50 megahertz. Today CROs you can buy, not the analog CRO, at least the digital CRO, up to 2 gigahertz. Of course, 2 gigahertz oscilloscopes will be very, very expensive. Okay. The moment an oscilloscope is built, right, there is one Y input and we generate a sawtooth waveform on the X to show that Y input, right. It could be for some reason I need to see one signal versus the other, right. I need to see what happens when I have an X signal versus Y signal, right. In such a case, the sawtooth wave generator and the trigger I do not need. I need another amplifier here, I call this as X amplifier and X input and I give Y input. Then I can see X versus Y on the screen, right. So, most of the oscilloscope that you have also has a mode, right, called XY mode. In the XY mode, the sawtooth generator is switched off, right. You give both inputs, you have to give as a user both X input as well as Y input. These are certain applications we will see later, right. Similarly, for my trigger circuit, I may generate the trigger from my Y input itself, so that I can see a waveform, or if I have my circuit and I have several points on which I want to look at the waveform, I would like to trigger the oscilloscope with respect to a reference signal, right, with respect to a reference signal, not my Y input, but some other input from my circuit which tells me that is my reference signal, right. So, most of the oscilloscope manufacturers provide on the trigger circuit to select where the trigger comes from, right. So, you can choose the Y, which means it is internally selected, the trigger input is internally selected or externally selected, right. So, if the external selection is chosen, then you have to give a trigger input. Okay. So, on the trigger again the oscilloscope manufacturers would give you a flexibility whether you want to choose the internal trigger or external trigger. In the trigger circuit again they will provide two choices called normal mode and auto mode, right. In the normal mode of choice in your trigger, you have to set the level and the slope, right. You have to physically vary the voltage level on the trigger and choose either positive or negative slope. In the auto mode, there is an internal circuit that checks for the your input waveform, decides what is the optimal level and what is the optimal slope for getting a repetitive waveform on the screen, stable waveform on the screen. So, if you put it in auto, you do not have a control on the level or slope of the trigger, right. Apart from this, there are other facilities given by the manufacturer of the oscilloscope we will see in the next class.